Um, Can all of you see the whiteboard?
Yes, sir.
Yes, sir.
Yeah, so essentially today you will continue the experiment that you did last time, and the idea is rather simple, and your seniors of course are more familiar with this subject than you are because we have not yet started the subject yet in the regular courses, but you can well understand the why are they waiting in the lobby? Okay. Okay, Arunakshu, I'm minimizing you now. You can start the lecture if I finish. Okay. Okay, so can you see the board? All of you can see the board?
Yes, sir.
Yes, sir.
Okay, so the idea is simple enough that we are going to talk about uh, uh, essentially enzyme kinetics, and as I mentioned earlier that there are many kinds of enzyme kinetics and we will be dealing with them later on. But right now we are actually, without telling you all the details, we will talk about the details later. Uh, can you put your volume off, Arunakshu?
Oh, sorry.
Yeah, yeah. Thanks. So essentially, you're all familiar with the essential argument that I have been saying, which is that you have the usual enzyme kinetics given by V is equal to V max S upon Km plus S. All of you are familiar with this. I'm just sort of repeating this. And obviously to find out these parameters, Vm and Km, these two parameters are what you want to find out from a data which you have got of S versus V. And different S values have given you different V values. And essentially, the idea is to find out the two model parameters Vmax and Km. And as I told you that there are various ways to do it algebraically as well as graphically. As far as the experiment is concerned, you will now plot it graphically, but I want you to think about the problem in more detail and in more depth, and think about what happens when the error is the error that you are trying to minimize when you are trying to fit, because otherwise just 2 points. Otherwise, just 2 points, 1 and 2, 2 points will solve the equation for Vm and Km. The whole idea of multiple points is to have regression analysis because there is an error associated and you want to minimize the error. Now, when you want to minimize this error, what is the error is very important. Where does the error lie? And is it proportional? So is this into 1 plus C? For example, if B is being measured incorrectly, or is it S into 1 plus C? These are the kind of questions that I asked you, but we will deal with it later. Right now, we will do a rather simplistic job, which is that we take the inverse of these functions, which is 1 upon V is equal to Km plus S. So we will forget all these things for the time being and do the simple things first, and later on then point out why these are not adequate enough, which of course then translates to Km upon Vm into 1 by S plus 1 by Vm. And as you know, this is the famous, many of you are familiar with this is the famous Lineweaver-Weaver plot, or the double reciprocal plot, and a plot of 1 by V versus 1 by S gives the slope intercept form of the equation, where the slope is Km by Vm and the intercept is, this point here is 1 upon V max. And of course, as I said, that the problem with this is that 1 by V is actually very small here. So when V is large and when V is small, then this 1 by V is large and your points are here. So these points, if they have small amounts of error, they would tend to damage this data very tremendously and give incorrect results of the parameters, because using these 1 by V max and Km by Vm, you actually find out Km and V max. So there are other plots available, and the most common thing is to take this equation here, this equation here, 1 by V is equal to this, and multiply it by S. If you multiply it by S, what do you get? So you get S upon V is equal to Km by Vm. Come on, I want some kind of response. Plus
S upon VM.
S upon Vm. Now, this what would you plot now? S by V versus
S.
S. So you plot S by V. So you plot S by V versus S. At least one double reciprocal is taken care of. And what would you get as the intercept? Now your intercept is different, right? So what is your intercept? The constant.
Km upon VM.
Yeah. And your slope is 1 by V max. So this is called the Hens plot. Okay. So this is called the Hens plot. Okay. And this is what you need to do for the data as well. And you have to see why the Hens plot is better than this data. And I want you to think and write about that. Why you think that S upon V versus S is a better plot than a plot of 1 by V versus S, and how is this plot of 1 by V inferior to this Hens plot? The other plot that is often used by biochemists, but that is usually used for protein binding studies, but we can use it for protein kinetics as well, is the ED-Hofstee plot. So this is the Hens plot, and now you can think about this third plot, and you have to think why these are better. And so the third plot is called ED-Hofstee plot, IE, I think, right? I mean, Ranamshu, correct? I've forgotten names actually. I think it's Hofstee, ED-Hofstee plots, which is essentially I multiply by this equation, this expression by VVM, multiply by VVM. What would you get? You will get VVM. So the first expression will become simply VM is equal to, please go on.
Km into V upon S.
So V upon S, okay, into Km, and then plus
V.
plus V. So what would you, or rather you can write V is equal to, or in other words, simply write V is equal to Vm minus V by S into Km. Correct? Simple enough. And so what would you
Yes,
plot? So you plot V by
We will plot and
V
V
by,
is V upon S.
yeah, we will plot this versus this. Okay, so V versus V by S, and again your intercept will be V max and your slope will be minus Km. And this is called the ED-Hofstee plot. And this is also superior to the double reciprocal plot. So these are two plots, these are three plots that you make. And now this is the three sets of plots, and each of these has different kinds of error distributions. And of course, this is a computer generated data, so really there will be no serious issues. But later on, when you do more complex models and actually do an experimental work, then of course this becomes quite different, right? And so now there are various, I mean, this particular experiment has also inhibitors, and I'm going to talk about inhibitors to you people later on. But essentially, what I want to tell you is that there are various kinds of models which explain inhibition, and I'm going to tease that later on. But I've taught your senior batch, so they are familiar with it. So inhibition kinetics, inhibition kinetics. Inhibition kinetics is what we are all going to talk about, and there are various kinds of inhibition kinetics that are available, and without actually getting into the details, because we'll talk about that later, I just want to tell you that V is equal to V max S as usual, and Km, the binding constant, the Km, which is essentially the proof of binding, because remember Km represents binding, actually changes due to the presence of inhibitor. So the Km becomes larger and larger, this is Ki, let us call it, as inhibitor becomes more and more, plus S of course. Are you getting this argument? So this is called competitive inhibition. Because the substrate, I mean, to put it very, the inhibitor competes for the enzyme, and so the ability of the enzyme to bind to the substrate, which is measured by Km, remember, the affinity of the substrate, that changes in the presence of inhibitor. And so Km tends to increase, which means that the slope will now become, the V versus S plot, remember, had a slope like this, where half the value was Km. Now, obviously, as you increase inhibitor, this will sort of tend to go like this. So you can see that Km is changing. So Km is becoming larger and larger with more and more inhibitor. Notice that with large amounts of substrate, the inhibitor presence is unimportant because substrate and inhibitor are sort of competing for them. Both are competing for the enzyme. So when you have huge amount of substrate, your velocity will be equal to Vmax. But at low amounts of substrate, most of the enzyme will be trapped by the enzyme. So as you can see that the moment the concentration drops, under normal situation, as the concentration dropped, the reaction rate would still be fast because it was binding efficiently with substrate. But in the case of inhibitor, you can see that here it is the same, but as it drops, you can see that the reaction rate is dropping because inhibitor is becoming important. And as inhibitor becomes more and more, so you can see, understand why it is called competitive inhibition. So it is called competitive inhibition, and we will talk about this in detail in the class. It is and so this is the equation. And I will leave it to you to do a little bit of algebra and decide what will be the double reciprocal plot or the LB-Lindbergh-Weaver plot. How will the Haynes plot look like? And how the Eadie-Hofstee plot will look like. That much exercise I think you can do. It's a simple, biochemists find it difficult, but for you people, it should be a cakewalk. Eadie-Hofstee plot, how will these plots look like for competitive inhibition? Where the Km values are changing. Notice Vm is unchanged and Km is changing. Km is changing, or rather I should call it effective Km. Notice that this is effective Km, right? I can call it Km star. For any particular concentration of I, this Km value, let us say if I is equal to Ki, then Km will become equal to 2 Km, right? So it will become double. So this Km is changing, Vm is remaining the same, and Km is really, this Km star is nothing but Km into 1 plus I by Ki. So how do you think the plots would look like when there is competitive inhibition? Because Vm does not change and Km changes. So look at your slope, does it change? And look at your intercept, does it change? This is a question which you can answer, right? Yes, no?
Yes, sir.
Yes, sir.
You can see the plots and you can look at them, and that this is a question that you should be able to answer. Similarly, in the case of, so you'll plot these things and you will use different inhibitor concentrations in the experiment. Find out which of these inhibitors act in a competitive fashion, which of these inhibitors acts in a non-competitive fashion or an uncompetitive fashion. So the uncompetitive inhibitor, on the other hand, and there is also non-competitive, which I will not talk about right now. There is no point boring you with competitive inhibition. Inhibition is where the plot, here the plot, uncompetitive inhibition is like this. Bm S upon Km plus S into 1 plus I by some K, let me call it K whatever, K small I, let us say. This is the kind of formulation this has. Now you have to think about what happens here. Does Km change only, or Vm, or is Km unchanged and Vm is changing, and so on and so forth. You think about this. Okay, and tell me then slope and intercept are changing or not. So this was very obvious, only Km was changing in Vmax. If the equation is like this, how do the slope and intercept plots change when with, so essentially my question is that here is a line. I'm not even saying what plot it is. Okay, now if the slope does not change, if with different inducer concentrations, you will get lines like this, changing I is changing. If the intercept does not change, then you will get plots like this. And I'm leaving you with this question, which is rather easy to answer, but I will not answer it for you, that if the intercept is changing, then you will get plots like this. Slope intercept is not sorry. Here the intercept was changing, slope was not changing. Here slope is changing, intercept is not changing, and maybe both change. Who knows, right? So you have to answer these questions as to which plots look like this with changing I, which plots look like this, and when in all those three kinds of models. So you have a series of questions to answer by actually doing the data plots. Okay. Am I going too fast or is it too complicated, especially for the first
No,
year?
sir. Sir.
हाँ, ये algebraic बताइए.
In our
Go ahead.
software, when we are changing the substrate concentration and varying that using with different concentrations of inhibitor, we are getting the same slope. There is no different kinds of slopes.
I do not understand what you are trying to say. Are you saying that you did different S values, found out your V values from your plot, and then you got S versus V for I is equal to 0. Then you do another
Yes.
S versus V plot for I is equal to 1, then for I is equal to 2, and so on and so forth, right? So
Yes, sir.
this is S, and then you see whether your slope is not changing or your maybe your slope is not
It is
changing,
not changing.
but your intercept is not changing. Are you saying that you get the same V by S? Your different S values or V is exact. This plot is exactly the same. It is the same plot for all inhibitor concentrations. If that is the case, then there
Yes.
is the inhibitor has no effect.
Slope is same.
Maybe then the inhibitor has no effect on that particular enzyme. That is the simple answer, right? But if it does have an effect, maybe you have different inhibitors acting on different enzymes. Some enzymes are not affected. Maybe you did enzyme 1, maybe when you do enzyme 2 or inhibitor 2, you will see an effect. So this is a large set of questions that you have, and I would suggest you go ahead. And this is mostly on your own. I don't think. Arnanshu, would you like to add a few words? And shall I stop sharing? Arnanshu, are you there?
Yeah, sir. Please, you can
So I will
continue.
stop here. I will stop here, and you please go to the program that you were working on. I will now get out. I will stop sharing. Okay. I will stop sharing. Clear the canvas. And oh no, what did I do? So you can now start sharing. I will stop my sharing. Sorry. So this is your content now. Sorry, you have to speak. You're muted.
Yeah,
You're
yeah.
muted.
I
So
will
now you can share the screen if you want to. I will give permission. Once again, hold on. Okay. Can you see whether you can present?
Yeah, I can present.
Yeah. Okay, so all you guys, now you know the problem. Arunam just display the whole thing all over again. The program that you showed last time, and maybe if you want to, in front of them, do one plot with one inducer concentration, one inhibitor concentration, and one enzyme to see how it looks like, and do just one plot. either 1 by V versus 1 by S or a Hens or an Eadie-Hofstee. Just do 1 by V versus S. The remaining combinations, permutation combinations have to be handled by the students while they are doing the practical. Is it all right? All of
Yes.
you? Is it okay with all you guys? Okay. So I will stop here, and I think Arunanshu, you can start sharing your screen and doing it. Thank you. Any questions?
Sir, I had a question. Like you said, there is uncompetitive inhibition and competitive inhibition. So, like in the software, when you put inhibitor 0, 1, 2, so how we know that we are working in a model of uncompetitive inhibition or competitive inhibition?
By plotting the graph of V versus
Link.
of V and S as a function of inhibitor concentration using the methods told to you just now. And depending on how the graph looked like, you'll be able to say that the inhibitor 1 was a competitive inhibitor, that inhibitor 2 was a non-competitive inhibitor. By actually plotting the graph and knowing how those graph patterns change with changing inhibitor concentrations. That is what I showed you.
Okay,
You
sir.
have
Okay.
to actually plot the graphs. Yeah. So Arunanshu, please take over.
Yeah. So everybody opened the last time, the one which the software.
Sir, can I? Yes, sir.
Okay. So today our exercise will be so last time we did the one with pH, right?
Yes, sir. Sir, I have a question.
Continue, please.
So, sir, here by plotting, sir, we don't have we all these plots are the slopes are same and intercept is also same. While what is called a product formed is changing with inhibitor concentration. So, uh, like sir is mentioning that like a slope should be different. That kind of graph we cannot get here.
I think, matlab, can I know your name, please, if you don't mind?
I am Ratnesh.
Acha, Ratnesh. Ratnesh, first of all, you have to keep your questions simple and concise so that people can understand. So you have to tell me exactly what you mean in a very short sentence.
Sir, can I show this plot?
You can show your plot. Okay.
So, sir, here intercept is also same. Intercept and slope both are same. Uh,
Okay.
but the but product form is changing. So V is changing.
Fine.
My question is that how can we get a plot for enzyme concentrations different and enzyme concentrations for which the slope these plots of at different concentrations are crossing each other at different at certain points means the slopes are different. That kind of graph we cannot get using this software perhaps.
Okay. So what you are doing here is that you want to know why the only why the product form is changing, not the slope or anything
Yes, sir.
else.
Yes, sir.
Okay. So first of all, then try to understand that this software is using the plot of what? Which equation? Have you figured it out?
Michaelis-Menten equation.
Okay. So Michaelis-Menten equation, it is trying to plot a Michaelis-Menten equation, right? Now what are the parts of the Michaelis-Menten equation when you plot?
What are the parts means?
When you are plotting, what is defining the slope of the plot?
Uh, it is being defined by like product formed upon this substrate concentration.
So in Michaelis-Menten equation, you are plotting V0 against S, right? To have that
Yes, sir.
kind of plot. Okay. So V0, what is
Yes, sir.
V0? V0 is the initial rate of the reaction against slope, against the substrate
No,
substrate
sir.
amount.
In Michaelis-Menten equation, we plot V and S, not V0, perhaps.
No, in
V.
Michaelis-Menten equation, we plot V and S, and when we apply the steady state concentration, then we go for no, in Michaelis it is V0 and S, and when we apply the steady state, then we go for V and S. I think that is the way. What is that called?
Sir, for a steady state, it should be V0.
Just let me check one second. Yes, in Michaelis-Menten, we plot V0 and S, right? And in Briggs-Haldane, which applies the steady state approximation, there we can replace V0 by V. Got it?
Sir,
Because initial.
Arnanshu,
Yes, sir.
can I interrupt here? I'm interrupting here. You see, don't get into Briggs-Haldane and Michaelis-Menten right now. Right now, keep it very simple. That plot is now all V0. We are all working with V0s, and V0 and the V are the same. So they are supposed to find out what is the function of V0 versus S. In a Michaelis-Menten, it is this first order going on to zeroth order saturation kinetics. And really what we are trying to do is to then take the double reciprocal plot and find out Vmax and Km.
Yeah.
That is all. So we are
Sir,
not going to tell them Briggs-Haldane here. It is
sir,
just
using this
whether.
software.
Ratnesh, the question that I am asking you is that when you use different substrate concentrations, then if you look at the plot here, can you see the plot on the screen?
Yes,
With
sir.
different inhibitor concentrations, your product formed is different. So
Yes,
how
sir.
can your slope be the same? Then how can the slope and intercept be all the same? I mean, this is illogical. हाँ देखिए बताइए कैसे है आपने कुछ गड़बड़ किया है अपने सॉफ्टवेयर में अपना जब आप when you are using your Excel sheet to plot it, you have made some mistake. See, these plots are very clearly different. This is a straight V versus S plot, which is very difficult to fit, but it can be fitted nowadays in software. So you don't have to do all those double reciprocal and Eadie-Hofstee and all these things. This is a fitting of the curve directly to the equation. But as you can see, these plots are different at different inducer concentrations. If the plots are different, then V versus S plots will also always be different. If the V versus S plot is different, then whether I am doing 1 by V versus 1 by S, or I am doing anything else, or V by S versus V, or whatever I am doing, these plots will have different slopes and different intercepts. So I do not understand what is your confusion.
Okay, sir. Okay, I will try to see again.
भाई आप कुछ गलत काम कर रहे हैं ना अदरवाइज ये V by S अगर अलग है तो बाकी प्लॉट्स भी अलग ही होंगे whether you do 1 by V versus 1 by S their slopes etc will change. So why are you asking this question? The plot here, the data here is different. If the data is different on V versus S, then the data on any plot that you make of combinations of V and S, whether it is 1 by V versus 1 by S or V by S or S by V versus S or V versus V by S, all these three plots will have different slopes and different intercepts at different inducer concentrations. And that will allow you to judge by doing your algebra at the back end that what is the nature of the inhibition and what is the inhibition constant. Okay, so please do
yes,
that.
sir.
Yeah. So Arunakshu is showing you a plot here. The software is generating different data. So why are you getting the same slope and same intercept? तो ये तो आप कुछ गलत कर रहे हैं ना. That is all I'm trying to say. Arunakshu, don't get into Briggs-Haldane, and that I will teach in the class. It is not part of this lab practical.
Okay.
because that is going to cause more confusion. Yeah.
Okay. So
I'll stop here. I'll stop here. Huh?
yeah. Okay. So what we are doing, what we were doing actually last time, what we did. Can I share now? Please stop sharing. Okay. So what we were doing last time was that we used that toy model software and we were doing that plots. So basically, see, the theoretical part has to covered by sir. So we are just trying to figure out how to plot those things and what you are going to make out of those things. Okay. So I'm not going into the details of that. So last time, as we all did, what was an enzyme kinetics, and we did what we changed the pH and we tried to see what are the different plots that are coming in. Obviously, these plots are open for interpretation to you, and you can always interpret and ask questions. There's nothing absolutely problematic about it. Now, the next thing is that today we are going to do another simple exercise. Is that we will now choose enzyme one. So everybody choose enzyme one. Is the software open? Everybody has the software open, no?
Yes,
In
sir.
their systems. Okay. So so you have to choose enzyme one. Then so last time, so I hope you have done the exercises for enzyme one. So what is the best range of pH that can be used for enzyme one?
It is 2
around
to 7.
4 to
So 4
Sorry?
to 5.
so 4 to 5. Like the optimal was around 4.6 something.
Okay, fine.
Yes,
So
sir.
put 4.5. Okay. So now the incubation time. What do you have put last time?
Sir, first of all, we have to define like what we want to vary today.
We want to vary just the inhibitor.
Okay, so first we have to choose which of these do you want to vary. So it is not like initially we have to choose pH of incubation time, amount of enzyme, incubation temperature, concentration of substrate. These
Exactly.
5 options are there.
So
So
you
what?
have to put all this because I hope you have, as an part of the exercise, you have already run it.
Yes, sir.
And now you know the values in which you get the best curves. So you have to give those values and then add an inhibitor. That's all.
Okay, sir. Okay.
So I am also parallelly running. So since mine is a Mac system, so I am running parallelly on a Windows. So please tell me the values. I am also doing it. So we are choosing
Okay.
enzyme one.
Yeah. One more point, Arunangshu.
Yeah.
All of you, that's actually that's for every one of you, all of you. Please remember that all of you have to submit your report now in Moodle. Both this batch. So this batch will submit its report in 433, the lab practical reports in Moodle, and the senior batch, which is only doing 433P, has to submit it in 433P. So please submit your reports, including the previous reports, in Moodle by 7th, because after that you will not be graded. So previous run all of you have done. Please go to Moodle and submit it, because we will grade it by. So the last date is 7th. Please check Moodle, and if you have any questions, send me an email or ask Arunangshu, and we will convey
So
it.
there's an issue with the Moodle submission.
Why? What is the issue?
So we have like including this week's report, we'll have 4 reports, but we can only submit 3
You
documents.
submit 3. Not this week's report. I will give you more time.
Okay,
You
fine, sir.
submit till the last week's report. You submit.
Fine, sir.
Okay, so 3 reports you submit, and this 4th report plus one more 5th report and 6th report. Again 3. I will give you a timing, or next week I'll give you time for the next 2. This report you don't have. This work will take some time, because it is a lot of graphs in each of them. Different inducer concentrations, different till pH and time and substrate optimization, which you have already done till last week, till that point, and the previous purification work and everything else, you submit these 3 reports you submit. If you want to, then please, I think these 3 reports are all. Today's work, you work it out, study it carefully, and I'll give you more time. So please submit it in Moodle.
Fine, sir.
Again, sir, in last class, like how many graphs we were supposed to plot? Like I have plotted for 50, 60, but more than that, like, is there must be some limit, like we can plot if we want hundreds.
Why do you want to plot 100 plots? What will you gain? The purpose of the work is to find out what is the optimum pH. Obviously, the first experiment you will do will be between 0 to 14 pH. You will get a very flat curve. From there, you will find out that pH optimum is somewhere between 4 and 5. Then the next graph you will do is between 3 and 6, or maybe between 4 and 5. And this narrow range, you will plot the graph, and that narrow plot is the final plot you will give. You cannot give each and every graph. Okay? Similarly for substrate concentration, similarly for time of incubation. You will plot
So I
the
guess in the
final
last class
graph.
you said
Which
5.
is, बताइए.
So you said like we have to submit 5 graphs per variation. Like we have to like keep all parameters constant, then vary the pH 5 times, and then submit it for the
Not
pH,
5
and
pH
similarly
5
for the.
times. You need to have, okay, hold on. Try to understand what I said. I said you need to have a plot which optimizes your pH well. Now, if you choose a pH range from 2 to 12, then obviously the software will choose very wide ranges of pH. Let us say it chooses 6 points. Then it choose 2 and 4 and 6 and 8 and 10 and 12. So you will know, you will get a graph which does not show you the proper optimum, because there is one at 2 and then one at 4 and one at 6. 4 and 6 may be equal. They may be higher than 2 and they may be higher than 8. But between 4 and 6, what is the optimum pH cannot be found out. So you know that your graph is giving you data for 2, which is very low, 4 higher, 6 approximately the same, and then 8 again lower. So you know that your optimum is between 2 and 4. Sorry, 4 and 6. Then you choose the range as between 4 and 6. And then you get something like much closer data points, so that you can find out the pH optima till the first decimal place. Does that not make sense?
Yes, sir.
Arunakshu told you this. Arunakshu has told this to you earlier. So I am repeating what he has already told you, if you were listening. And so suppose your optimum is 4.5 or 4.6. You report that and show the graph which proves that it's 4.6. That way I already know that you have done first 2 to 14 or 2 to 12 and found out the optimum is between 4 and 6. Then you have done a narrower range between 4 and 6 at more closely spaced pH points, which is 4, 4.2, 4.4, 4.6, 4.8, 5.0, 5.2, 5.4, and so on and so forth. And therefore, your narrow range has allowed you to select the optima better. If someone has found out that it's between 4.6 to 4.8, then you do between 4.5 and 5.5. And then you have an even narrower range, and you can then finally find out that the pH optima is say 4.65 or something, or 4.55. The more you do it, the more narrower the range, the closer space the points, time points of experimentation, and the better is your optimum. And you put the final graph only. Same with,
Yes.
Same with other. So this is what is expected out of you. I want you to write your report in 3-4 pages so that it is readable. Theoretically, only 55 or 60 people attend, but the remaining half of the people don't even attend. Please don't copy from each other, because we will know. Okay, and just submit.
So one more
4 or
doubt
5
I had.
Yeah.
So regarding the temperature curve, since the temperature would like the optimum temperature would depend upon the incubation time. So like can we just keep a constant incubation time for each assay? Like say 10 minutes or 20 minutes.
This is something which you have to think. This is where a good quality lab report differs from a bad quality lab report. And you think about what I told you about temperature optima. Obviously, higher time points would reduce the temperature optima. And so the true temperature optima will not be caught very well. So these are the questions that you have to think and answer and write. So you just don't plot graphs. When you plot a graph, I want a paragraph in your own words as to why this graph is like this. So when you do a 10-minute incubation or a 5-minute incubation and you arrive at a temperature optimum of 55, and then you do a 25-minute incubation and you arrive at a temperature optimum of 50, then why has that changed? I want an explanation from you guys. Because that is what is the part of the lab. I mean, otherwise, if you're not thinking about the data, then you're not even doing the experiments because of online, then what are you learning? This is precisely the objective of the lab report. You understand? Lower the, smaller the time point, 5-minute time point, you will get a higher temperature optima, slightly by a few degrees.
Yes, sir.
And very long
but like,
incubations, you will get
how do we how do we basically judge that which incubation time is the best then?
there is no such thing. There is no such thing. There is no such thing as which is the best incubation time. It depends finally on the purpose. That is not your job here. For your job is to find out the enzyme characteristics. Obviously, we are not here talking about enzyme deactivation. Yeah, go ahead.
Incubation time can't be more than 60 minutes.
नहीं, आप इतना लंबा नहीं करिए. हाँ, ये meaningless है. हाँ, this is a meaningless exercise doing it for more than 60 minutes because substrate will be exhausted. Temperature enzyme will be deactivated. So in the last, from 30 minutes to 60 minutes, it is not going linearly. The plot of P versus T, I talked about this in the last class. The plot of P versus T, the slope of dP by dt is equal to V. If dP by dt is not constant across the incubation time, your data is wrong. It is simply wrong. Do you understand? That is why Arunakshu was talking about V naught. Because P versus T is what generates V. But P versus T should be a straight line for the period that you have taken the time. If you do a 60-minute incubation, your P versus T is not a straight line. So dP by dt is not a constant. Then what is the velocity? But we are interested only in the initial velocity. So you should keep times small. You should keep the time points very small. Okay? But not so small so that there is error in measuring P. Yeah. So please keep P values and write a sentence that I chose different time points and I got different lower values of V by V because dP by dt was declining, and instead of taking the tangent to the line, we were taking the chord because P final minus P initial divided by total time. That is the chord of a curved line. The chord of the curved line is obviously lower in slope than the tangent at the start of the curve, unless the line itself is straight. Do you understand the sentence? Did you follow? Or should I draw it again?
Yes, sir.
You fine, good. Yeah. So you cannot take 60 minutes where from 30 to 60 there is hardly any change, and that has been incorporated in dP by dt because you have divided by 60 and you have taken P minus P naught, P minus 0 actually. ये तो बिल्कुल सारा डेटा गलत हो गया ना. So your time has to be chosen carefully such that dP by dt does not drop precipitously because the later time points there is no substrate or there is no product formed because of enzyme deactivation. So you have to choose small time. अरे भाई वो आपको पता है क्या अभी से?
Sir, I did plot that.
So then you plot it, and then from that plot see when the straight line starts curving down asymptotically and flattening out. Then you say ki, well, I will not choose any time more than this point. That judgment call if you have taken, please write it in your report that I tested for different times, found that dP by dt was declining, and it was declining very sharply at when I took long time points. Therefore, the maximum time I can take is 15 minutes or 20 minutes or 25 minutes or only 10 minutes. That depends on the enzyme. That depends on the amount of preliminary experiments you have done, again through the software. Okay?
Yes, sir, yes.
Okay, thank you. Now I will not say anything more, but please submit your previous 3 reports on Moodle, both batches, please. Thank you.
Sir,
there is no much
yeah,
more. Yeah, you just do concluding remarks and we'll wrap up. Let them do the experiment.
I think, sir, we can show at least one curve with the data. Matlab, they can have.
Yeah, please show one curve and then and please let them do the experiment. It is not your job to do the experiment for them. Just demonstrate one. Okay, thank you.
Okay. So like we were using a software, it's just toy model, and we are not understanding whatever. Okay, many a times we don't get the feeling how we are getting those plots. Okay, so for your pure interest and in order to demonstrate and to make things interesting, I am showing you how the plot has been how the plots are generated and with a real-time data. So many of the data you are putting in the software are actually you are putting it on your guess or you are trying to figure it out. But what happens is that in most experimental condition, your guesses are not actually sufficient or our guesses are not actually sufficient. So let us at least see one data which is right and with which we generate a plot. So everybody good with that?
Yes, sir. That will be good.
Okay. So I'm sharing my screen. So my screen is visible now?
Yes, sir.
Yes, sir.
Okay. So let's, I will start here. So this was the book I also told you at that time. So you must all be having. So now you see this, now you can see the problems. Problem 8.1, an enzyme catalyst reaction was found to be affected by two inhibitors A and B. The following results were obtained at fixed total enzyme concentration, right? Everybody can see the data. Substrate uninhibited with 1 millimolar inhibitor A and 1 millimolar inhibitor B.
Yes, sir.
Okay.
Yes.
So you can take a screenshot also with the data, or you can take a mobile screenshot and use this data also. Okay, to get a feeling of how the things will go. Okay. So again, you will be using Excel to do the plotting. Okay, and I am showing you on the thing with which I am comfortable with. I generally do it R programming, so I'm showing you one plot. So here we go. So now you can see that I have already loaded the data here. Uh, the substrate is this one, S. Everybody can see now.
Yes, sir.
Yes, sir.
So you copy this. Don't go to the programming parameters that you will learn. So I am simply like as you put the values in the x column, I am putting that thing. Okay. So I have put the values of x column, and now I am using the uninhibited data for this. Okay. So these are the data for uninhibited. So I am using again this one, going back, command V, enter. Okay, so there's a small error. This should be comma. Okay, what happened there? So I have loaded the two values, the substrate concentration and the we are now looking at the uninhibited one. Fine. So now I use different parameters to those things. So I am getting. So you can go to if you are interested in doing R, there are plenty of blogs available, and they generate real-time programming data, share programming data. You can just copy it, paste it. So now you can see we have used S as substrate and we have used un for. So this is V. So we change it to un. Right? Everybody following?
Yes, sir.
So
Yes.
Sir, we have to make these plots in Excel.
You can make it in Excel. I'm showing you in R where you can. Excel is actually Excel is good because you can plot with R. If you learn a little bit of R programming or any programming, you can crunch your own data. So I use R, so that's why I'm showing it R. You can do it in Excel, right?
Sir, so we have to not build these plots in Enzyme essay, right?
No, you have to build that. I am showing you in order to make you understand how things go with the real data.
Okay.
Okay, so now I have written the command and now I hit enter. So now you see this is the MAC list maintain,
Yes, sir.
right? I am sure demonstrating these plots to you in order to understand the example given in the book is a real-time data. So what happens is that with real-time data, in a practical class, you are supposed to come to the lab and generate your own data and work with that. But since we are not doing that, we are using a virtual platform. So the software, what you are doing is actually you are trying to make an intelligent guess. But many times your guesses doesn't work and you end up with something which is actually something inconclusive. So I'm showing you something that can be conclusive so that you can generate, you can have the interest and you can have the crunch that how things are getting. Okay. So now I will go for the Landweaver and Burke. That was the Mike list maintain part. So again, I change the V to un. This X lab means level of the X axis, Y lab means level of the Y axis. Main is the Landweaver Burke. This is the function I have already defined. I have given it the equation. And these are the points are colored as red, so we call it color as blue. This is PCH is the point value, how much big the point should be. These are all these things, so you shouldn't be worried about it. So again, we hit enter and we have the Landweaver Burke. Everybody can see the Landweaver Burke.
Yes, sir.
So in Landweaver Burke and Mike list maintain, I hope you understand. It is nothing. Landweaver and Burke just reversed the parameters in order to have a linear graph. And if the data generates a linear graph, that means the assumptions or the hypothesis of Michaelis-Menten equation are valid, and the Landweaver-Burke that is, well, you can apply the Michaelis-Menten equation for that particular enzymatic reaction. But if the Landweaver-Burke plot is not linear, that means the assumptions of Michaelis-Menten equation was not valid. As simple as that. Understood?
Yes, sir.
Sir, like in enzyme assay, we only make the plots between pH and time and between substrate and time. So how we will plot the velocity versus substrate in enzyme assay, that enzyme assay?
Yes,
Software.
sir. This question should be answered.
One second, please. Slowly.
Sir, in enzyme assay, like we plot pH and versus time and substrate concentration versus time. So in enzyme assay, how can we plot velocity versus substrate in enzyme assay software?
Sir,
The one
actually
I am
there we have only product and substrate all the time. And that change
so that is a different kind of software in which they are plotting product. But originally, in when you are working with with your real-time data, you will be mostly plotting the velocity and the substrate, because you see that the velocity of the reaction all over the reaction course is not the same. So people are interested in measuring the initial velocity, which can be determined precisely. But that is giving you some pH and all those things and all those data you are plotting there. So that is your part of the exercise. I am showing you how these plots are generated, because there you are making a guess. And now here we are showing you how real-time data can be plotted and these things are generated.
so, sir, how can we get the data so that we can plot in Excel as sir mentioned? We have only this enzyme assay and we can plot in only this. So what to do?
So I showed you now one data. I told you to take a screenshot of that, and now you can use that data to plot in Excel.
Okay, so sir, we have to use the data you shown that.
Because it will
and
be
nothing
easy.
more.
It will be easy for you. Because if you are
Yes,
not getting with the software, which I don't deny, because it is possible, because you are guessing all the time. Maybe pH 4 to 5 will be right, maybe this will be right, but they may not be right. So this is a real-time data which you have to use, and you have to use your brain to find out that how you use this data. Got my point?
Yes, sir. So for last experiment, we have to use this software Enzyme assay, and for this experiment, we will use this data that you have shown.
Yeah, no. First listen. First, your primary work is with that software. Now I have given you a data. You go and plot it in Excel, and you try to find out the different parameters by your own. That's how you grade the crunch, how things are going. And now once you understand how things are going, you can move on to the software and generate the plots and give an interpretation what actually happened from the software result. Getting my point?
Yeah, sir. Perhaps we will plot, then we will understand.
I understand that is that is one of the that's a really a painful part of it that I appreciate your concern. But right now, like, we don't have much to show, because if I go directly to handling this softwares, I hope then you have to learn programming, and you have to then again go and do all those fittings and all those things, which sir doesn't want you to do at the time. He just want you to, like, first review your situation and try to do simple problems and then go on to the more trickier one. If you jump to those trickier one at the very first time, you will be missing a lot of fundamental things that you can understand by doing things by yourself. So can you see the see my screen? Problem
Yes, sir.
8.1.
Yes. Yes, sir.
So you can take a screenshot of it in your mobile. And use this data. And I have already told you about this book. So you can go to, everybody of you know Library Genesis, right?
Yes, sir. We know that.
So you can download these books and get this data and work on your real time. So whatever you submit, if it is concrete and if it is logical, even though it is wrong, it doesn't matter. It is good because you have shown your effort and you have done the exercises by yourself. That is all that matters. So let's go back to our original thing. So I will just now switch it.
Sir, can you go to that page? One second. I want to ask something. Like the readings that you showed, substrate, uninhibited, and yes, sir. What is this uninhibited column? What this shows? Uninhibited.
Uninhibited means there is no inhibitor added. With 1 millimolar, that is A is your inhibitor.
And sir, this is a concentration. 0.684 is the concentration of the inhibitor. Means 0. What is this 0.684?
This is the velocity of the reaction.
Okay.
Right. So you can see it is written initial velocity absorption per. So this is the initial velocity, and this has been determined using a spectrophotometric method. That's why this is absorption units per minute. Okay. So now let us go back to our original exercise. If anybody of you are good enough, so we go for enzyme A, right?
Yes, sir.
Inhibitor A, right?
Yeah, sir. Inhibitor A.
Okay. So first we put enzyme A, okay. Then we press OK. So which of these do you want to vary? So what you want to vary, pH of the incubation or incubation time? So let us avoid pH. Let us not complicate the matter. Let us first the incubation time. So how much time you are going to put? Somebody give me a figure here. Give me one number.
Sir, incubation time like 30 minutes or 40 minutes.
Okay, let's put it 30. Okay, so minimum is 30 or maximum is 60. Use these values. Okay, amount of enzyme 100 microliter, we keep it unchanged, right? Temperature is 30
Yes,
degrees,
sir.
we keep it unchanged. Substrate concentration, we keep it unchanged at 100 millimolar, and now we set inhibitor A. Okay, We put a concentration of 0.125 to 1, the first option, and we perform the incubation. So the curve has been generated for everyone with this number.
Yes, sir.
So that's typically the exercise we are talking about. So don't change the pH, because if you change too many things, you will be not be able to comprehend what has happened. Basic. So you just change inhibitor concentration again and again and try to find out how the inhibitor concentration is affecting your plot. And obviously, see one more thing important is that most of the time when we, as a biochemist, when we do these experiments, we generally talk about substrate concentration and initial velocity. That's the way we learn this thing. Okay, so now these guys are using something which is called the product generated. So obviously there are people have used different approaches, so that is perfectly good with it. So you can figure out how this product formed can be uh, converted into initial velocities or something like that, to figure out that how these curves actually make sense to you. Because I also, the fact is that I have never used this product formed. Understood?
Yes, sir.
And sir will guide you how to comprehend this values and how to read through these figures. So I will tell you one example how this can be related. First thing is that, see, if you are studying in physics, then the sign of the work done and heat, they are completely different what you study in chemistry. So this happens all the time in science, so it is not a big deal. So you have to do what you have to read through the things what sir wants you to do. I am just telling you what to use and what are the values to be used. Okay, and if you further have some problems regarding this, you can always ask me or sir.
Sir, we have to also plot this graph in a lab report, like this product versus this product versus this this product versus this plot of enzyme assay.
Yeah, whatever you do, keep a record of that with yourself, and at the end of the day, what you are going to analyze, and you are going to have a conclusion, right? So you write your conclusion and the figure from which you have concluded. Not to take, you have to do thousands of experiments because before you actually have a success with it. So whenever you present it to someone, you don't show all the experiments, but it is understood that you have done all those experiments in order to reach the goal you have reached. So you have to give the final one from which you are concluding and your conclusion. That's it. Got it?
Yes, sir. Yes,
So
sir.
we'll
Yes, sir.
end
Yes,
it-
yes, sir.
We will end it here,
Okay.
and you have to do the experiments. Arunangshu made a very important point in the end. I hope you understand that your velocity is actually dp by dt. And really the velocity that you're interested in is the initial velocity. So ideally you should do the incubation for 5 minutes only. But then if you do the incubation for 5 minutes, then measurements in P are very small, so there is a lot of error. So we do it for 30 minutes, and if the line is curving downwards, then dp by dt is not equal to v naught. It's not equal to the tangent in the beginning of the slope. And so when you do it for 30 minutes and you are calculating velocities and making the plot which actually assumes initial velocities, there will be error. And I want you to write something about it from an independent experiment which you don't have to show that what happens when I find out P for 5 minutes and what happens when I find out P for 10 minutes, because every time it is P by T, and P by T is approximated as dP by dt. And P by T is equal to dP by dt only when the P increases linearly. That much all of you understand. So the initial velocity, which is the tangent to this curved slope of P versus T, is incorrect because you report P by T as dP by dt because you say that is V. You take the product form, divide it by time, that's P by T, and you say that is equal to dP by dt. That may or may not be true, as he said. And I want you to do an independent set of experiments and say that, well, dP by dt is approximately equal to P by T when we do it for 10 minutes. or it's still approximately equal to, because the straight line P by T is still equal to dP by dt even when we do it for 20 minutes, and so on and so forth. So these are the background experiments that he was talking about. And the main job is, of course, to find out V. And after you find out V, you do all the things that I talked about to find out the inhibitor constant, the Ki and the Km and the Vmax. Okay. So we stop here, and you have to do this report over the next week. The report, previous 3 reports, you have to submit in Moodle very soon, within a week. So I've given you enough time. Is it all right? Arunanshu, can we end it here? Yeah, thank you.
I am
Please
done.
go ahead and please go ahead and do these experiments now. We will, do it on your own laptop and submit
So
the
just
report.
a
Thank
second.
you.
So for this week's report, could you just give us like one line aim? What exactly are we supposed to do in this week's report?
This week's report is very simple. One line aim is find out Vmax, Km and Ki, and whether it is competitive
Fine.
inhibition or uncompetitive inhibition. And does
Fine.
the data, does the results change if you use a Eddie-Hofstee plot or a Haynes plot or a 1 by V versus 1 by S double reciprocal plot? If it changes, why does it change? And why did you choose a certain time point? You see, these are the comments that you have to make.
Fine, sir.
And why did you choose
Fine.
a certain temperature? Yeah.
And yes, sir, and apart from that, a summary of what we did, right?
Yeah, obviously, that's obvious. Yeah.
Yeah,
So
okay.
the summary of what you did was, it will be the plots, but every plot should be accompanied by a small, short couple of lines, a short paragraph saying why you think this graph is like this and how it could be better or what could be wrong with it. That is what Arunanshu was trying to emphasize.
Fine, sir. So
Okay,
basically,
I want an
we have to
analysis.
find the
I want an
kinetic.
analysis. Yeah, you have to determine the kinetic parameters, and you have to tell me what is Vmax, what is Km, what is Ki, whether it is competitive or uncompetitive. But beyond that, you have to also make a comment about the data. Why do you think it is a good data? Why do you think it is reliable data? Why do you think it's unreliable data? Okay, that comment shows whether you are analyzing the data blindly, mechanically, or seriously. Okay.
Fine, sir.
So let us start. Yeah, thank you.
Thank you, sir.
Thank you, sir. Good afternoon, sir.
Thank you.
Thank you, sir.
Thank you.